where it could go. Then I thought, like, instead of having these basic terminologies, what about let me give a clarification on this, and then go ahead with new topics that you will be interested in. Next slide. Okay, the next one is very important. Whenever we talk to an amateur astronomer, he says, okay, that star, the planet is -4th magnitude, the star is magnitude 1. What is this magnitude? Where is this word magnitude coming from? What happened is people wanted to know about a comparison. When you look at the star, you wanted to compare the brightness that you can see from a star. So it's as simple as this. I have a bulb here, and I have, say for example, the screen that is lit up. You can now compare how much light is coming from the screen versus how much light is coming from this bulb. So you have a ratio of the screen is say about 100 times lesser in brightness than this bulb. So you have a scale. You take one star as a reference and you take another star which is 100 times more. Now if the difference in the first star and the second star is 100 times more, then we call it as a magnitude 5 difference. If 1 and magnitude 5 are 100 times in difference, that means the first one and the next one in between would be 2.25 times the previous one. So you have to put in 4 different stages. The first one is magnitude 0, which you say x times. The next one would be 2.5 times that x number, so that is magnitude 1. The next one is 2.5 times, 2.5 times the first one, so it becomes 6.25 times the first one, and so on. So it gets multiplied. You multiply this by 5 times, you get close to 100, because 100, fifth root of 100 is 2.5. So that is how all these calculations come. I am not going to explain you that. What I want you to understand is this. The magnitude 0 is taken by a reference star, which is Alpha Centaurus. Alpha Centaurus is again a nearest star to us. Then we have, on this scale, this is a magnitude scale, and you will see that there is something called an apparent magnitude. Apparent magnitude is as simple as how much you see. It's not the original. If I press the same bulb, say about 50 meters away from you, the intensity of the light that you get, the photon that you get, will not be the same. So you will not see as bright as it is now. So this difference, depending on you are looking at a bulb and eliminating the distance factor, okay, that is what is called the apparent magnitude. So you have an apparent magnitude. That is what matters to us. What I see coming from Earth is mattering to me that this whole star is big or small, or it is energetic or not. So we have an apparent magnitude scale on which Alpha Centaurus is at 0, and Sun, the brightest object in the sky, is what about 24 to 26 magnitude. So you see that it is -24. That means in the magnitude scale, the negative numbers means brighter objects. So you are getting towards bright objects as your magnitude scale says 0. And as you say positive number, it gets dimmer and dimmer. For example, you take a Bernard star. Okay, so the Bernard star is somewhere around 9.5 magnitude. That means it is, you have to multiply 2.5 into 2.5 into 2.5, 9.5 times, so much dimmer when you look at and compare to. And Sun is so many times more bright. On this scale, it is very important to note that we can see all the way from Sun to a limit which we call a naked limit, and that is about 6 magnitude or 6.5 magnitude. Why am I asking you to give an attention to this is, when you go out for observation and you look at the sky, if you are in a very good place, in a dark, isolated place with a proper dark adaptation. Dark adaptation is, you sit for a while looking at the sky, make sure that your eye, everything is opened up right, so that your eyes are sensitive for faint lights. You know, I give this example. You are in a bright light outside this room in the sun, and you immediately come into a room. For a few minutes, you feel like everything is dark. do not switch on the light, stay there about 5 to 10 minutes, you will see that the room is getting brighter and brighter. That is only because your eyes, the pupils in the outside area where the brightness was more, it controls the incoming light, and as soon as you come inside, that does take more time to expand. So this time is what we usually have an adaptation period. So we have to adapt to the night sky during the observation. And when you do proper adaptation, you will see a star up to magnitude 6. But there are lots of other problems. No matter how long you adapt in the city, because of the light pollution, you will not be able to see the stars. No matter how long you adapt yourself for the night sky, if the sky condition is not good, you will not be able to see. So, not just your adaptation, but also the sky conditions, the locations, does matter. Okay? Now, as you get on, you can see that the magnitude 20, the plus 20 magnitude is the limit for a 1 meter telescope, and plus 30 is the limit of the Hubble telescope, Hubble Space Telescopes. Hubble Space Telescope is in space, and that's about 2 meters. But if you notice, its sensitivity is up to about plus 29 to 30 F magnitude star. What it says is, all these ground-based observatories have the problems of the sky, the atmospheric turbulence, and the atmospheric air presence itself is following the observation. So the moment you go over, it's an absolute space where nothing is going to spoil the observation. So you will adapt it to higher limits. Okay. You can notice that the full moon is about 12.5 magnitude. Just do a calculation. I am not showing a calculation. Just do a calculation of 0th magnitude to 12.5 magnitude. How many times moon is brighter when it is full? And a cratered moon would be somewhere around -2 or -1.5. It would be that the crescent moon would be very much less in brightness, apparent brightness, than the full moon. You will see that the difference of the object's brightness itself vary every day. Okay, this is a typical spectrum of a star. So, what you do is, you look at a sun, take a grating, and you take a spectrum. Spectrum is nothing but an experiment where you split the constituents of the incoming light and then capture what are the signals. This is a specific typical star spectrum. This is for a sun. And you notice all these lines. These are the signature. We call them a signature of the elements present in the sun. And these are the signatures of the elements which are showing their presence in optical. Now, studying this kind of a spectrum led to the discovery of helium. Element. So, why I put this is for you to understand that it is not just observation. As an amateur astronomer, you could also take the spectrum, you could analyze and contribute to that. So this is the spectrum. I just want you to understand that there is lots of signatures, but one point is, if I have so many elements in this, then why do I use a radio spectrum or gamma ray or X-ray? You know, there is X-ray telescope looking at sun, there is a gamma ray telescope looking at sun, there is radio waves looking at sun. Why do we look at different frequencies? Because each of these frequencies give you different layers of the sun. That's what it is. This is a typical sun's photo. Not related to amateur astronomy, but still to explain certain concepts on the observation. The core is the hottest, where the nuclear fusion is taking place. As you come out on the surface, you have about 5,700 to 6,000 degrees. And as you reach this point, as you come out, each layer, the convection zones, then the coronal holes, the chromosphere, even to be outside the corona. See, there are lots of different rays. There are X-rays being emitted, there are EMF sun's parameter. So now it depends on you to choose whether you want an optical or a radio or an X-ray, whichever field you want to get. But all you are going to do is study the same object but to wide spectrum. Okay, this is where I give more importance for amateur astronomers, because the moment you want to look at the sun, okay, most of our observations will be on optical vision. So the moment you make a filter, use it through your telescope, look at the sun, you will be able to see certain parameters on the surface of the sun. Now, 5,000 to 5,700, 6,000 degree Kelvin is somewhere in the peak of yellow. That is why sun is yellowish in color. Now, when you look at the sun with the filter, all you can see is the surface. You cannot get deeper into the surface of the sun. So your optical medium or an optical telescope can only tell you parameters that are visible on the surface of the sun. So if you want to study the core of the star or even the layers within the star, you cannot use optical. Now, we will concentrate on what is on the surface. On the surface, you will see what we call a coronal loops, which bump up from one of the sunspot to another, the poles of the sunspots. Okay. So basically, the energy gets transferred from here to here in big loops, on the surface of the sun. This is a comparison. The Earth is this big when compared to the coronal loops. So you can understand how massive these loops can get. This particular slide is to explain you that when you look at the sun on the filter, always with a filter, if you get to see a coronal loop, then you can estimate what is the size of the loop, how much time did it take to come up. So you can do an experimental observation. Okay. So this slide says that you have an observational project where you look at the sun, measure the height of the coronal loop, and you can do actually the height at which this is going and what time it starts, what time and how is it working. Okay. But this is not a disadvantage. You know, the sun is this sphere. If you at all you want to see a coronal loop, then these loops have to be at the surface. They cannot be on face on. So that's a problem for amateur astronomers. If they are face on, you cannot see them. They have to be on the spherical, this circumference. It's the same thing for the next object, which we call the prominences. Prominences are again coming back. See, this is one photo of the sun. There is no prominence. As time goes by, you can see there are some small energy particles, high energy particles somewhere, and here you can see like this. That means you can also observe prominences. The same conditions apply. The prominences, if there was one which was coming right in front, we wouldn't have known this. But if we have to see through optical, then we have to get it into very close. Well, if optical can be used only for the periphery of this sphere, then if at all there is a coronal ejection, mass ejection, or prominence coming face on, how do you detect? You detect through different mediums like the X-rays, gamma rays, or radio rays. Each of these also will have some signatures of these spectrals. When you study them using different telescopes. So you use different methods to study different regions of the sun. These are sunspots. Okay. Typically, most important for any students doing a project or amateur astronomers interested in having the life cycle of the sunspot. These are dark areas of the sun. They typically look dark because they are relatively cooler regions of the sun. Why are they cooler? Because like you take a red hot burning charcoal, spray some water on it. Though it is red hot, the points where the water falls becomes dark. It becomes black. That is exactly the situation here. Though there is nobody pouring water there, but the situation is relatively the temperature is going to go down. And those relative temperature differences will make it appear dimmer and darker. Now, this slide will tell you that this is a surface phenomenon. So, you with a telescope and a proper filter can actually mark these sunspots and study them. So, it will be a study and observation project study. So, you look at the sun on a specific day and then you look at it after some time. These sunspots, if they move, you know that the sun is moving because it is a surface phenomenon. If they don't, then you know that it is a localized phenomenon. We will talk about how to do this small projects in the second half of tomorrow. I will be discussing tomorrow about projects that each one of you can do. Interesting factor. You know, these sunspots have a cycle. Cycle in the sense, their activity goes to a maximum at some time and they drop down to minimum. Means at some point of time there will be lots of sunspots on the sun's surface, and at some times it gets gradually decreased to zero. The last 6 months to 1 year, we had absolutely no sunspots on the sun, and we were expecting it to be growing, okay? But we did not find any in the last 6 months to 1 year. But now it is gradually started. What happens is that is what we call a maximum and a minimum. So each one of these spikes is a specific year, and you can see that 1800 to 1850 there were 1, 2, 3, 4, 5. That means there were 5 spikes, 5 times the solar activity raised to a peak and then dipped to the minimum. This gives you a 11-year cycle on the sunspot. So sunspots gets peak to maximum activity and drops down every 11 years. And there are certain times when there is absolutely no sunspots. For example, if you look at this, from 1600 to almost 1700, 500, there were minimal or absolutely no sunspots. And this region, we call it as an ice age region. I don't know whether it is related to sunspots or not. It is observed that during that period, the polar ice caps of the sun or the earth, they grew a lot, and they were actually environmental changes that came up during that time, which affected the poles of the earth. Because lots of ice was gathering there, and lots of environmental changes happened during this period. And that is why this was called an ice age. And after that we did see, but it was actually a scaling point, because this ice age also repeats every few 100 to 1,000 years. And we expected that since we did not see anything in 2009, 2010, it could be the beginning of a start of an ice age again. Okay? Why? Because lots of myths you hear about the doomsday and other things.
So, what is the ice age got to do with the sunspot number?
Yeah, we have absolutely no idea why, but we have just seen a correlation there. During that time, there was an ice age. There is no correlation that is found on the.
Okay. One more question. When the sunspots come on the surface of the sun, does the intensity of light radiated by the sun or the power radiated by the sun goes up or goes down? Is there a variation?
There will be a variation.
So maybe that is related.
We don't know. We don't have a direct correlation between the ice age and the sunspots or activity, but it is observed. So I don't comment anything on the physical aspect, but it is observed. Now, this slide, see, every slide I have an activity for you to note down and do as an amateur. Why I have this slide is you can make your own sunspot cycle records. So you start observing sun from now, and it is hardly about 10 minutes job every day. Set up a telescope, look at sun, mark how many sunspots do you see. Go back next day, do the same thing, repeat this over a period of time. After 11 years, you will see that the number of sunspots actually increased and then it went down. This is what exactly you were saying, the activity going high or low. This is sun in radio wavelength, okay, where the high energy particle that has been radiated has been captured, white in this period, and as the cycle increases, the sunspots increases, it becomes very energetic and very active. So this photograph is the cycle of sunspots again in a different wavelength, not an optical, different wavelength. Then comes the color. Now, you just go in a observation site, look at the sky, you will see different stars with different colors. The red, the blue, the white. Where does this color come from? So, this is a chart which I wanted to explain. The apparent color that you look at, the color that you look at when you are looking at a star, is directly related to the temperature on its surface. For example, if you are looking at the sun has typically yellowish color, so it is about 6,000 degree Kelvin, and a red star would be much lower, like 3,500 degrees Celsius. As you get higher in temperature, surface temperatures, it gets changes in the color, wherein you get white during 10,000 to about 8,500 and bluish as 700. So you have different colors in the stars only due to the surface temperature differences. The material inside will be the same, but the nuclear fusion that is going on is absolutely still the same, but the surface temperature determines. Now comes another question. If it is the surface temperature that determines, does it tell anything about the cycle of the star or anything about the surface, the life cycle of a star? Yes, it does say about the life cycle, because if the size of the star blindly expands, then the color changes, because this overall surface area is going to increase and the temperature is going to drop down. So the temperature difference also depends on the size of a star and its stage in life cycle. So let's look at that. Before that, as an amateur astronomer, this is a picture which I have just put to show you that there are different colors in stars. It's very evident. This is a blue star, this is a red star. So the temperature on this star, can anybody guess what is this? Orion Nebula. Yes, Orion constellation. This is Orion Nebula. This is Rigel. This is Betelgeuse. Okay. Betelgeuse is a red star. This is a blue star. So this is a special method in photography that we take. I will explain this later. But this is a picture that I want to show you that there are stars in here. Now comes the life cycle. Our topic in between this discussion. Only because I wanted you to understand the size, the age, and the temperature does matter for color. Let's just scan through this and then see how things change. In the universe, we have nothing but hydrogen and helium gas floating around. Absolutely nothing should happen if it is uniformly distributed. But the universe does not have uniform distribution. There are some places where there are ununiform or disrupted regions. Those regions get together, the cloud in that region or the elements in that region, hydrogen, helium, they combine and they get attracted to each other with gravity. This forms the very early stage of the sun being formed or star being formed, which is called a nebula, pre-star nebula. Then when the sun is, when the star is, the core gets heated up as the material comes to the core, the temperature increases, the star is born. When the nuclear fusion takes place, the star is up. And I want to introduce you a word called main sequence star, which I will explain in the next slide. So the star is born. Now, depending on the star position, usually it is about 6,000 to 10,000 degrees centigrade. That means yellow star to a blue star. Now, when we see a yellow star, when the mass of the star is as compared to the sun or 1 or 2 times the sun, if it is higher, the 3 to 5 times the mass of the sun, then this star, which is still in a born state, just a blue star, it could be in a blue color. Okay. Now, the blue star or the star which is massive, it becomes a red supergiant as time goes by. The stage from this point to this point is about about, say about 100 million years. Okay, because the bigger stars burn out the fuel faster, and the star which is the comparable age of Sun, from this stage to this stage is about 10 billion years. Our Sun is a 5 billion year old, so the Sun will still continue to be the same size, the same weight for another 5 billion years. After that, what is going to happen? The Sun, which becomes a red giant due to the expansions of the outer surface and molecules, then explodes as a nova, which forms a planetary nebula. So a low mass star becomes a red giant and then becomes a nova. Explosion occurs and then becomes a planetary nebula, when the surface materials gets thrown out into the space and the core becomes a white dwarf. Okay? And this white dwarf, this cools down and it becomes a black dwarf. This is on paper. If you ask me, can you find any black dwarf? I will say no. Because from here to here it is a 100 million year circle. From here to here, it's hardly any time, okay, for an explosion. And the moment this is formed, a white dwarf is formed at the center. From here to here, it takes about 100 billion years. The whole universe is about 13.5 billion. So expecting a star in this age is not feasible. There is no star in this particular life cycle, in this age. Because it takes about 100 billion years to get to this stage. Now come to the next cycle, which is bigger. The same nuclear fusion takes place. I'm not going to go into the details. The star becomes red supergiant. And the red supergiant star, when it explodes, you have a process which is known as supernova. So in the supernova, what happens is, exactly the same thing happens similar to the nova here, but it explodes in such a way that it creates all the high energy particles are thrown out, and these interact with the surface materials on this star and the interstellar medium. That is where all the high elements apart from iron is being formed. Like most of you are wearing gold. Every element of the gold that you are wearing has come from some star in the universe being exploded as a supernova. This is the only source of the gold being formed, or even anything else, platinum being formed. So every part of gold in your body has come from some star dying. So you should be proud that you are part of a star. And as this explodes, there is two stages. One is it gets to a neutron star or a black hole, depending on the mass of the core. Let's not get into details. This is 3 times the mass of Sun, and this is more than 3 times for ourselves. But for amateur astronomy, we don't have to worry about this. On a general note, when the supernova explodes, most of these materials, the star has hydrogen, oxygen, nitrogen, all these elements in the chemical table. All these things during the explosion merge onto the interstellar medium. A star explodes here, and there is a cloud of new star being formed. This particle is just spread across the universe, gets combined with this, and that is where the new star forms. And these elements, heavy elements that we extract now, are part of this. So this process would have taken maybe a few billion years from materials coming from here to our solar system. Let's go to the next one. We learned this life cycle. Why I explain the life cycle is to explain you the temperature differences and the size. Okay. Now, I was telling that when the sun is formed, when the star is formed, okay, I will be using sun and star as a interchangeable because both are same. When the star is formed, it can be anywhere between this point to this point, and this is called the main sequence star. So if the sun or the star, when it forms, it is a very small mass, then it becomes a N-type star or a red star, and will occupy this region of the main sequence. If it is a sun type, then it goes and occupies in this region. the other star which is Betelgeuse. Betelgeuse is occupying here. Betelgeuse is here. You notice that Betelgeuse, okay, I'll explain you this. The star forms on this, it grows and then it takes a shift towards the first half of the curve. This is a life cycle. The star is formed and then it takes a shift, it becomes a supergiant, this is a supergiant, and then when it explodes or when it vanishes, for example, a giant becomes a white dwarf, the curve comes down. It's a very interesting chart which is called the chart diagram. Combines lots of things. The type of star, the temperatures of the star surfaces, and then it also calibrates how many times the luminosity is. It's brighter or dimmer, all these things. Let me not complicate you this. Assume this. We have x-axis in terms of temperatures, and temperatures have associated colors with them. You see sun. Sun is typically about 6000 degrees centigrade. So you look out for this, and then there is sun here. Dark. And then you look out for another star, its temperature, there's it here. Depending on the light cycle. But you can see that this region is red, so as this region. What is the difference between this and this? The age. Now, you have to understand that our old star, which is big, is also red in color, and a new star, which is small, is also red in color. Because a big star has low surface temperature, a small star does not generate more energy internally, so it is still giving low surface temperature. So these two will be on the same y-axis. Now, you can always say that Betelgeuse is a old star and it is not on the main sequence, so it has completed its 10 billion year cycle, already gone. Since it is a supergiant, okay, it cannot be a 10 billion years because it's a massive one, so it has to be less than that. It could be somewhere around 1 billion or 500 million years. Now this cycle will tell you a different points. You just pick any star that you know. You just pick any stars that you know. You will understand that the I'll tell you the temperature also. Just any star that you know, if I can find out here. Any stars? Name of the star? Sirius. Sirius is here. It's a blue star. Surface temperature about 10,000 degrees. Arcturus, a reddish yellow. Surface temperature around 5,000.
Pole star?
Pole star is Polaris. Okay, this is Polaris, yellow color. Temperature about 7,000. So any star you can position with this temperature, age, and you will know what is the age, how is it like. The next step. Let's check out as an amateur astronomer certain things in the moon. The very prominent one is the crater. You can see that an impact craters on the moon. Another one is these big empty regions, like an ocean park. I don't know whether you pronounce this as Maya or Maria, but always remember that these are another structures that you can study as an amateur astronomer, and the craters. To the next slide. Can anybody guess what is that? Yes. The next slide. Next one. A Q star. It's the near side and the far side of the moon. How many of you have seen this? Most. How many of you have seen this? None of us would have seen this because the moon is tidally locked to Earth. Moon is tidally locked to Earth. Means one phase of moon, that is that phase, is always looking at the Earth, and the rotation period, the moon goes round on its axis, and the period that it takes to go around the Earth, both are absolutely the same. So as the moon goes around the Earth, it also rotates on its axis, and since the speed is the same, it That is why you will see always that phase of the moon, not the other one that I showed you. Now, when you look at the full moon, you can only enjoy these areas, but you will not be enjoying the craters. You will not know the beauty of the craters that are on the moon. So for that we have one more technique, or we advise you to look at different time zones. Okay. I'll come to the observations of craters next. Before that, you have to see that why are these phases formed. I'm just giving you this to understand that we have the light coming from the sun being reflected onto reflected from the moon, giving us the phases. So, for example, the moon is here. Half of it is always lit. Okay, this side is still moon's day, but looking from this Earth, since it is tidally locked, this is not visible. This is still a day, but not visible. Many people misunderstand this region to be the far side of moon. It is not. It is just the near side of moon, which is not getting. This is the day time of the near side of moon. This is the night side of near side of moon. Okay, and this side is far side. This side is the near side. Now, I will just give you one more example. Moon takes approximately 28 to 30 days to go around. What is one day on moon? What is one day on moon? How much is one day? One day on moon is 30 days of Earth, because the moon's rotation and revolution are both the same, so it has to take exactly the same time. So one day is 15 days, one night is 15 days, approximately. Which most of the full moon. Okay. When you are observing moon, it is very important that you observe these craters at the edge of the moon being lit and these places, because this will give you its shades and you will study the craters and its beauty better. If you are looking at the full moon, the light is directly falling onto the crater and then you are receiving back, so these features are lost. But when you are looking at the side-light illumination, so these are more prominent for you to study than this. And we also have a shine. When the sunlight falls on the moon, you get the phases, but the sunlight falls on the Earth, and this gets reflected and falls on the moon, that gets reflected. That is when you see this vision. So this side of the moon is lit because of the sun light reflected to the Earth's surface. It's you take a picture of moon on any given day, take after 6 months, the size of the moon will be varying. And especially if you want to take it up on two different positions, that is the nearest point and the farthest point, then you have a big difference in the size of moon. This directly tells you the orbit of moon is elliptical. And we know that there is a tilt in the moon orbit, and that is why every full moon and the new moon does not give us an eclipse. If the tilt was 0, every time the moon comes in between sun and earth, it should have been a solar eclipse. But we don't get that because the tilt is here. And if you go back to astronomy, we call these points as nodes, but in astrology they call it as Rahu periods, which will be more familiar to you. A simple structure to explain you that solar eclipse is just a gauge plate between the moon, earth and sun. It's three people independent of each other, a pure coincidence that gives rise to solar eclipse. I always support solar eclipse. I encourage people to go ahead and look out for solar eclipse, lunar eclipses, because the moon is positioned exactly in a region where it can cover the sun. The apparent size of this moon and the apparent size of the sun, they are the same as seen by the earth. Sun is 400 times bigger than moon and sun is 400 times away from us. That makes them both equal as we see from earth. When we have this rare combination, one passes the death of the other, we get an eclipse. Now, such that this combination will not happen. So we humans are at the right time of a solar system, of the age of a solar system, when this rare combination is happening. And this is giving us to study the external features of the sun, coronal features of the sun. So never ever miss this opportunity, because 25,000 years from now, I don't know, even if you are alive or get cut, it's not going to be visible. This is a lunar eclipse, the shadow of the earth, but this is a phase of moon. You have to know the exact difference between the eclipse. Guys, I love rumors. Okay, most interesting rumors are Mars coming close and appearing as big as moon, and then you get an SMS saying that midnight 12 o'clock you see 2 moons in the sky, so 2 suns in the sky, so get up and see the rare event which will never happen in your lifetime. You see the comet or asteroid is coming and hitting the earth and will all be gone. Doomsday for 2012, so many things happening, the earth positioning, all nonsense. And then finally eclipses. Never look at an eclipse. They give out some invisible radiations that can spoil people. Absolutely nonsense. But I love all of this. You know why? Every time somebody gets this message, I get a call. Naveen, I have this message. Is it true? Can I know more about astronomy? Can I know more about sun? Can I know more about the moon? So people get curious about Mars, about their distances, about their information, and they come back to us as an amateur astronomer. Not just me, all my friends get this call. So I think most of our amateur astronomy club people will have this call. Okay, so we become famous during this time. So the more we have this kind, I would love it. Okay, but these are all rumors. Please do not get onto them. Just here, get to know certain things about that rumor, and then. Okay, I'm done with this. Any questions on that? We have a solar filter. Okay, we have a sample. I'll take a break. You can see the solar filter, and we will give you the details of the solar filter. There are solar filters.
You mentioned on the chart, representing the temperature. What is the name I'm repeating properly?
HR diagram. HR diagram. Yeah.
How is the moon perfectly phased out?
Okay, that's a coincidence. I have absolutely no information on what is the physics behind that being exactly phase loss. All we know by observations and theory is that it is law. I am only talking about the observational aspects. So it is phase law. How do you understand that it is phase law? By observations. Maybe it is in gravity of the area of. Yeah. What I would say in physics terms is the moon is exactly at the position and the speed which is required for its rotation, tangential velocity as well as its on-axis rotation is almost the same. That is why it always runs in the same channel. I'm not sure of
The direct correlation between luminosity and age is there.
Yes, it is.
I mean, but you also said that supernova would be of the same color as a
supernova is not the same color. The star that is about to explode as a supernova is of the same color as the supernova. So it is a red giant and a small star which is red in color. The red giant, after it explodes, it's going to occur as a supernova. Because it is higher on the axis. All the stars which are above the main sequence, they have finished their. Okay, I'll explain you this. What is this main sequence in the diagram? Main sequence is that star whose core is burning helium, hydrogen. The moment the core turns to burning anything apart from hydrogen goes out of that main sequence. So Betelgeuse is not burning hydrogen in its core. Betelgeuse is burning heavier